We've had two papers on GenSci looking at various aspects of the practical side, and I'm very pleased to invite Bastian to take the stand to tell us a bit more about some of the scientific aspects.
So, yeah, thank you very much. Yeah, good morning, everybody. Yeah, as already introduced, I'm talking about the scientific perspectives and possibilities of GenSo. We have heard quite a lot today already, so I go through that quickly. Well, GenSo will interconnect several hundred ground stations all over the world. We've heard that with thousands of participating non-commercial spacecrafts. And now we get into the interesting part. Several tracks of each spacecraft every day form several thousand passes, even with a lower number of ground stations. Let's say 100 ground stations and 20 spacecrafts form 2,000 passes, and you have several passes a day, so you get up to a really huge amount of passes you have. And what's now interesting is that you can utilize GenSo for doing more than just collecting data or sending data up to spacecrafts. You can collect, and we are going to collect, information about every pass and its link quality and report it to the GenSo authentication server and collect this data. So we collect several thousand pass quality reports every day. This is a very huge amount of information, and I will show you today how we can utilize that to optimize GenSo and optimize satellite space links in common. The pass report database we establish, which collects all this information, is, as already said, used for network optimization and a manifold of scientific investigations, and it is offered to the public so that you can head for it and utilize it to make own scientific investigations on it. So what you have already seen is you have the ground station server, you have the mission control client connected over the internet, and you have this authentication server, and I name it here core database cluster. This is where all the information is collected together, and you can interconnect the research subsystem to make investigations on that. And that's a very interesting part, because it offers you a huge amount of data about spacecrafts coming along passes, and you can, yeah, oh, sorry, what's going on? Yeah, you can make your own scientific projects utilizing this data to optimize satellite communication. So what information can be derived from receiving communication links, which is known as passive links in our network? It's the bit error rate, the BER, the packet loss rate, the PLR, a signal-to-noise ratio, and a spacecraft tumbling rate. So this sounds quite cool and quite easy, but the problem is that it's quite hard to derive that information, because the only thing you can really do is to collect S-meter readings, or if you are aware of the data, the bit error rate. But you are not aware of the data in advantage, because GenSo is passive from the perspective of all the links it's utilizing. So we only know that there is a pass coming along, but we are not aware of the data within the pass. So we can't say if the data is valid or not. What we can do is, if we are aware of the protocol, we can say if the data, if a packet was valid or not. Or in the case of forward error correction, we can probably say it had that amount of bit errors, but it's very rough. It's not very precise. So what we are going to do is we utilize the signal-to-noise ratio to derive the bit error rate. And from the bit error rate, we can derive the packet loss rate. But yeah, as you will see later on, it's anyways quite rough. What you can also do is to find out the space tumbling rate by utilizing the S-meter readings, as we can see on the next. Oh, on the second page. So this recorded link information shows you exactly the S-meter reading during a pass. So this is the information we collect during every pass, and this is the one we use as a base for further investigations. So now this is from the AAUSat-2 satellite. What you can also do is to derive the tumbling rate by reading the S-meter reading. So that's quite interesting, because you're aware of what your spacecraft is doing even if it hasn't ACDS on board. So what can this information be used for? What you can do is a rapid spacecraft orbit determination offset detection. I will get into this a little bit later. You can do a spacecraft pulse quality prediction. You can predict the ground station quality. You can do a spacecraft communication and power system health determination. You can reduce the packet error by data overlapping. And you can determine yet mostly unconsidered link quality affecting parameters. Because what we are going to do and what my PhD is about is to find out which parameters except the communication parameters really affect the link. So I'm going to build a prediction system where I can say, okay, the quality of a path will be that and that based on our past examinations on that. And this can be things like the weather and that kind of stuff, but I'll get into that later. So what is this rapid spacecraft orbit determination offset detection about? It's Ivo Klinko who is in this with his master thesis. It is intended for a quick determination of spacecraft TLEs after launch. It scans a supervised TLE and frequency variation different for every ground station. So what we are going to do is we say we have a predetermined TLE from NORAD or calculated on our own, and we slightly differ this TLE and give it to every ground station so that the ground station will point probably to the wrong TLE, but probably to the very right TLE. And we are going to analyze the quality of the downlink we get from beacons and can therefore determine the TLE very quickly. So the different measurements are evaluated, and the one with the highest quality is assumed to be the most correct TLE, as already mentioned. And this will shorten time to get into contact with the spacecraft after launch from several days, probably worse, down to a couple of hours. And this is very interesting because the first hours of the deployment are the most critical ones for satellite missions. With all ground stations within a spacecraft's ground track deliver worse quality than predicted, whether the orbit offset raises or the spacecraft has communication problems. So therefore we can detect orbit offsets and correct them during the normal operation of GENSO, even before NORAD is able to provide actual TLEs. So now more details about this spacecraft path quality and ground station RX quality prediction. We are going to form a model for the prediction of future passes, and this is derived on the collected quality reports, as already mentioned. What we are going to do is to also consider environmental variables like the local and space weather, and also concentration of gases in the atmosphere and things like that. The optimization is that it avoids the waste of resources by booking only passes which are predicted to have a high link quality. So we can determine if a link, let's say in 2 hours over a specific ground station, will be of good quality or not. And if it's not of a good quality, we probably book the ground station for something else or take another ground station for an active uplink. So this is some kind of quality insurance we get into the network, and it significantly raises the quality you get out of it. So the nominal RX quality for a ground station can be predicted so that if a ground station delivers significant worse quality than other similar ground stations, the station is most obviously miscalibrated or has other hardware problems. So the benefit for you is when we get the path report handed in by you and we find out that it's of not a good quality, then we can report that to you, and then you know that you have probably a hardware problem or your station has a miscalibration. So how does it look like? We utilize the spacecraft and ground station radio data from the authentication server database, the local and environmental weather and space weather information web services, and they hand it in path link quality. So we are going to data mine that using technologies with machine learning and derive a satellite path prediction model. And this is going to be used to detect the ground station quality, to make a satellite path schedule decision, and to make satellite power indication. Because a scenario is if the quality we derive from a special spacecraft is lowering continuously over several days or weeks, but the ground stations are okay because they are all determining this lowered quality, then we can predict that something with the power on the spacecraft is probably wrong, or with the communication system. This is very interesting for spacecrafts which do not report about their health status. So This passive solution we are going to implement has one big disadvantage. It only analyzes the received data. It's because we don't get any feedback from the satellite if the data which has been uploaded through one of our ground stations has been of a good quality. Another problem is the difficulty of result comparison between different spacecrafts, because different spacecraft use different frequencies, different modes, different protocols. So it's quite hard to compare these different parameters. So we are heading for a quite novel approach, the design of an RX-TX quality measurement satellite for non-commercial ground stations in LEO. With other words, we are going to implement the first orbital measurement and calibration instrument for ground stations. Yeah, well, this is, to get a little bit into detail, it's a separated project. It's based on GENSO, but it's not, GENSO is not relying on it. It's more in addition to it. So it's a prerequisite to get reliable space-link quality assurances, both RX and TX. It makes scores of new methods for enhancing space communication available to the community, and it's free of charge for all participating ground stations. So how is it going to work? We are going to implement a satellite, or a satellite cluster, which is going to measure the quality of ground stations by sending a predefined bit sequence down to a ground station intended to be measured. The ground station is sending the bit sequence, including all the errors without error correction, to the GENSO authentication server, and it forwards it to the evaluating ground station. The ground station is going to inspect the data downloaded from the spacecraft by the measured ground station and finds out the bit error rate, a detailed one. So you get a detailed evaluation feedback for your ground station for a specific pass. And GENSO also gets a feedback so that we are aware of the quality of the ground station and can consider this in booking. What we are also going to do is to provide the same for upload. So a ground station which is going to be measured or would like to be measured is sending a predefined bit sequence predefined beforehand. The measurement satellite is saving the bit sequence on board and transferring it down when being over the evaluation ground station. So the bit sequence sent up to the spacecraft is sent without error correction, so you will most probably have a lot of bit errors in it, and will be sent, including error correction, back down to the evaluating ground station. So we can precisely say what bit errors have been within the stream. Again, we have a detailed evaluation feedback to the GENSO network and to you as a ground station operator. So some of the planned applications of the measurement satellite are a fine-grained quality information for already presented prediction models. So we are going to refine the passive prediction model I've just presented before and make it more detailed and more precise. It offers the immediate detection of any calibration or hardware problems of ground stations. It provides a detailed feedback several times a day about the condition of your ground station. And the detailed information about the ground station's availability and condition is flowing back into the GENSO for the booking algorithm. So when we are aware, probably before you are, that your ground station has problems, we take it out from the booking algorithm so that a critical mission operation is not going through a ground station which has possible problems. It ensures an optimal possible link quality in both RX and TX for all participating missions in GENSO. Well, this one is legally probably not that easy, but we could offer the emulation of other spacecrafts by having a software-defined radio on board to approve the operational readiness of the affiliated ground station before launch. So you can say, I would like to test my ground station for the spacecraft which is launched, and we are going to change frequency and mode to the spacecraft you are launching, and you can test your ground station if it works properly. Well, as I already said, it's probably legally not that easy, but the possibility is given. What we also can offer is a fully featured link quality history for every participating ground station operator and mission. So you can get a history over years how your ground station did work and how the satellite worked. And we have an automatically calculated communication range for every ground station by evaluating the link quality for every ground station angle in detail. So you have a rapid detection of unwanted elements in field of view, example given a broken tree after a storm or so. because we measure the bit error rate not only for the whole pass, but for parts of the pass. So we know exactly in which part, at which angle you had a higher bit error rate than in other angles. So what's the current state of the sub-project? We have initialized cooperations, for example, with the Aalborg University. A journal paper will be published soon covering the design. The project proposal is currently in review state from the Austrian Council of Science. And the decision is awaited for October 2008. The estimated project start would be January, and the estimated service deployment would be the end of 2010. Well, that was about the satellite we are going to design and probably going to build, especially for GENSO and for the community joining GENSO. And there are other topics which are of scientific interest within GENSO, like performance analysis, performance model engineering, and the simulation of the GENSO network, passive and active satellite pass booking scheduler. This is quite sophisticated and very sophisticated when you take the quality determinations into account, because there are many factors which are going to affect a booking, because you have probably 100 ground stations within the range of a spacecraft, but only one of them can make an active upload. So this has to be decided on a very sophisticated base, and this is also worth scientific work. We are heading for a Java-based protocol transcoder. We already have some for KISS and AX25, but we would like to have one for every common protocol like FEC protocols within GENSO, which would be very great, but it's really hard to achieve. It's a Java-based software radio framework, so that we are not relying on external solutions which are not platform independent. And what we are also going to develop, which is also quite scientific, is a framework for local and space weather data collection aggregation, which is used for the pass quality prediction. Yeah, so what we are looking for are scientific and engineering people who are interested in doing scientific work on GENSO. So we offer scientific topics for your bachelor thesis, master thesis, or any engineering practical course. So what we think is that GENSO has a really high scientific potential. We just need people who are interested to investigate in that. Yeah, we would really like to see you in the project. Yeah, more information can be found on the GENSO project website, as already presented today. The scientific coordinators are myself and Lars Mehnen sitting here. So don't hesitate to come to us, contact us if you're interested to do some scientific work on GENSO. Thank you.
Thank you very much, Bastian. A completely new dimension I hadn't even considered that the GENSO technology could achieve for us. Do we have any questions? Yes, Florian.
In fact, it is not a question. Bastian, for your space weather data, please contact ESA and its space weather data infrastructure that is called SWEMET. They will surely help you in providing all the data.
Thank you very much. Any other questions?
Yes, one. The network's based on trying to calibrate out lots of different spacecraft with different modes. Would it help you if there was a set of what I would call beacon satellites, just one satellite with a very consistent, well-known power beacon on each of the bands as a genuine calibration source for the entire network?
Well, that's exactly what we... Oh, that's what you mean. Well, it is, because what we can say is if your ground station operates well on another frequency than our spacecraft, but what we can see is if your ground station is well calibrated, and if the amplification works, and these kind of things.
What you get is relative measurements on, but you're coping with different spacecrafts. What I'm saying is, if there's a absolutely known reference source, would that make your life easier?
That's exactly what we are heading for. That's the idea of the measurement spacecraft. So that's the reason why we came to this idea at all, that we say we want to have one absolute reference, being our spacecraft, where we are totally aware of the state, we are totally aware of the power, and we exactly know the bit sequence, the bit stream which is sent down, and which is...
Yeah. What band do you plan to put that spacecraft on, frequency band?
UHF mainly, but we are also thinking about making a cluster where we have different, or cluster is probably the wrong word, several spacecrafts, where the first spacecraft, it would be a CubeSat, where the first CubeSat will be equipped with a UHF transmitter, and the following spacecrafts could also operate in VHF or S-band. So we think about covering several different bands.
Yeah. Oh, interesting.
Right, if that's all, then everybody goes to say thank you very much, Bastian.
Thank you.